So yeah, this is how this works. We all mask up. We all try to sit as far apart from each other as possible. The MacBooks, or the little iMacs, have been updated to Big Sur, so it's all up to scratch. They have Python. They have all the stuff installed. Who here has ever done anything in Python before?
Ever or never?
Who here has programmed, did some computer programming at some point in something, right? We've all done a little bit of this, yes. Cool. I'm sort of assuming absolute base 0 entry level. So if you have done my 390 class, some of this stuff is going to be very familiar, and some of this stuff is going to be super easy. It doesn't stay there. I just want to start there. So the very first assignment is basically, oh, look, programming, hello world, all that good stuff. By the end, we'll hopefully do some machine learning on your computer. So that's the idea. Research method is an incredibly broad theme. I thought, yeah, come in. I thought we cover most of it. It's programming, data visualization, how to fit a line, how to fit data, because I'm a very practical scientist kind of person. You throw data at me and I model it, right? So that's where I'm going to be talking about most. However, there's some other stuff that you also need to do that kind of falls under the giant umbrella that's called research methods, right? Writing is another thing that's part of research. It is a ridiculously large part of my job. When I was your age, I would have never guessed the fraction of time that I spend writing English. So I'll talk about that next week, right? How to set up your writing, how to set up your literature review, how to set up your system so that you can keep tabs on all the references that you're using, because scientific writing is completely different from, say, an English class. And there are some excellent writing classes on campus. Go take one. They're free for you for, like, if you're in grad school. There's some writing groups, etc. Go do that if you want to write faster. But what I'm going to talk about, especially next week, is mostly the how to set up your literature, how to keep tabs on your literature, how to organize that, right? Some general use there. OK, so this is me. Hi, I'm Ben Olverda. I'm a professor here. I'm an astronomer, so I'm just massively slated towards astrophysics as far as my biases go. You can always email me. We can do office hours by appointment over Zoom of Doom. And then I don't have a required text, but there is a text in the Blackboard for the second half of the class. This is mostly machine learning. A friend of mine she's writing a book about this, and she was nice enough to actually go like, right, well, I'm here on this page today, so here you go. This is where I'm at right now. And so there's not really a required text, but there's some suggestive text. So today we'll talk about how the class works. And so it's very much like 390. I see a couple of 390 veterans here, somebody who's been in my 500 class. It's very similar. I talk one class. We work on problems the other class. So we got the first Jupyter Notebooks. The Jupyter Notebooks are all neatly in every week. That's not to say that you can't work ahead. Go ahead. In fact, this is the class you can have finished by midterm. And I'm good with that, right? So you can have all this stuff done and focus on the other grad classes. I'm fine with that. But I want to introduce you to Python, and I'm going to talk why Python and why I'm doing that. But also, I will be doing this on Blackboard Collaborate on Thursday. So I'll be here to help. I can do this in person, but I can also do this on Blackboard Collaborate. And in fact, if nobody shows, I might just do this over Blackboard Collaborate and just be done with it, right? So. But I don't want to assume that everybody has a computer. Who here has a good laptop or has a laptop that can run Python at home? If you don't, we have machines here. So I'll open it up, and you can work on the projects here. OK? So the other thing is that I have one. So every Tuesday, I go over a topic. Every Thursday, we go over to Jupyter Notebooks. Everyone picks a recent paper. And so here's the good news. Pick one that you're already going to do your PhD in. You probably have gotten a paper assigned by your advisor. Go pick that one, right? That's perfectly fine. Double up the work. That's cool. But I do want you to see if there's anything that is like either a data visualization that you like from that, or, and especially because this class is more about the new kind of data analysis, machine learning, if there is a paper on the topic that you are interested in, say you say, like, I want to do quantum vision, whatever that means, right? There is a there's a paper that says machine learning in the title. I'm going to go pick that apart. That's what I want you to do. That's the final, okay? And then there's class notes in Overleaf. I want you to learn how to write LaTeX. And some of you have worked with me on LaTeX. Some of you know what LaTeX is. Some of you who here has not ever written anything in LaTeX. Right? LaTeX is our, it looks a bit clunky. It's a bit old because it's from the 70s, but it is fantastic for things like scientific writing. It is very good for anything that has equations in it. It has every math symbol known to man, and then some. And it is very good in dynamic referencing, which is something that I'll talk about next week. But essentially, it allows you to forget about which papers you actually cited in the paper, in the thing that you're writing. It doesn't require for you to go through the entire text one more time to go like, wait, did I cite A. Abrahams once or twice or what? Right? All that stuff it does automatically for you. It is absolutely great for writing a thesis in, because you want to get all that stuff handled, like all the dumb stuff you want to have a computer do, and this is what LaTeX is good for. So the class setup, Tuesday is the lecture. This will be recorded. I hope you're being okay with being recorded, because you know that this corner here. Oh, I'm actually out of the screen, but I'll be hopefully standing about here. I'll be recorded, but if you ask questions, hopefully you're fine with being recorded as well. And I'll be here in the Thursday in the teal room. Please do not eat, or especially not drink in the teal room, because you know we're precious. So you know keep away from that. That's a hard rule. Lots will be very unhappy with me if I don't enforce it. The COVID rules. Well, we're all happily wearing a mask. We're all 6 foot-ish from each other. Clean the workspace after you're done, especially if you work with a computer. Do everything hand it in through Blackboard, because there are assignments. That's pretty straightforward. You can also email me, but I prefer Blackboard because then I can actually see where everybody is. I will be adding you to 650 once the Blackboard people are okay with that, so that I can just communicate through this 650 channel. All the permission forms, stuff that needs my signature, etc., just email me, because I do everything electronically, and if there's one positive about this whole thing, I never have to touch a piece of paper ever again. The masks are mandatory. Again, you don't have to be here. I know this movie came out well before anybody here was born, probably. But if you haven't seen The Princess Bride, you know, do yourself a favor and watch a classic. You can't possibly have got to the end of Netflix just yet. This is the phrase that I think has now taken wing here in Kentucky. Please use it when I do something silly. We just say, we can't be doing that. Like we all kind of huddle up over one monitor or something. Let's not do that. Let's get through the semester healthy. Okay, so textbook 1 is the one that I use for 390. And this is very much like, hey, let's get started with Python. Hey, let's get started with programming. It's written by a grad student. This is how the best stuff gets written. It's a grad student that gets annoyed by the fact that there is no documentation, and then they write everything down that their friends told them, and then you end up with this, and it's awesome. So that's one. And the second one is this by Viviane Acquaviva. She is super happy with any comments. So if you hand in a PDF with like little scribbles and notes with like, hey, this is not how you say that, or what does it say here, or anything like that, I will happily give you an extra credit or a pass or something, because you know that we can use feedback. This is writing a book is hard. You're all going to write a book. It's called a thesis. And as it turns out, it's really hard. And then we do it ourselves again. So Jupyter Notebooks are the assignments. That's the main thing. What's that? Again, you should be able to do them on the computers here, but if not, then you can do it at home. And the main thing is to have Conda, or I use a Conda installation, Conda flavor of Python. Python there's different ways to install it. I just use Conda. There's other ways. Please don't make me help you with that because I have no idea, okay? I'm not a computer scientist in any way, shape, or form. Most of this stuff, however, is still plot x versus y. It is basic programming for most of this because I want you to think about the stuff that we're doing. I don't want you to spend an afternoon trying to install the latest of torrent or whatever it is that you need for this, right? So I want you to get some understanding of the various codes. I get to Google. Yes, you get to Google. Absolutely, you get to Google. This is not stuff that I memorize, ever. I still Google the same 5 things over and over again because I keep forgetting what the actual phrasing is. So yes, please, please, please get into the habit of like first asking Google and then asking a friend and only then throw up your hands in. A new language without documentation is really hard, and we're going to learn a new language here. Python is a language. It's a fairly easy to learn programming language, but that doesn't mean that you're going to be it's going to be easy. The skill levels are going to be all over the map here. I know this already, so I'm just assuming the absolute beginner at the beginning, and it's going to be a little steeper for some and a little slower for others. If it's too easy, work ahead. There's already somebody who's cheerfully chucking in all kinds of Jupyter notebooks because he's going like, hey, great, I'm going to be done by the halfway through the semester, and I'm fine with that. Asynchronous means you can be working ahead. That's why I stuffed every Jupyter notebook already in there. I worked rather hard over the Christmas break to make sure that everybody can do this right now. There's not going to be a crunch for this class at the end of the semester. For me, maybe, but not for you, right? I may have to grade stuff, but that's it. So the goals are really, we have data in the physical science. Unless you're some paper and pen theorist, which is a vanishing small part of this physics, you got data and you have a model that you want to compare that to. So you want to compare the models. You have a theoretical model, or you have something that you want to compare to your data. You have predictions that you want to make based on said model. You want to evaluate what your data quality is. You want to compare models between each other, and we want to figure out how to work that. And we want to convince others that our model is the best model. And you can stand up here and say, oh, my model is the best model, but it really helps if you can show rather than tell. And that's where visualizations come in. And I want to talk about the new analysis, which is machine learning. It is rather something that I'm learning still, so I will not pretend that I am a absolute expert on it. It is something that I've looked into for astronomy from time to time, but it's really taken off right now. So we'll learn together there. Okay, so model versus data. We've got models. The models are well described with known parameters. They have zero error and uncertainty, and they have infinite precision. Basically, I can tell you exactly where my model is going to be. Why? Because I don't have any noise in there. Not even the precision of the computer, maybe, but that's about it, right? I know exactly where it's going because it's a line, and that's perfect. The data are the points that I'm trying to model that, put the model to. That's the empirical part, and this is the theory part, usually in physics, right? And so they always have a noise component in the data. There is no noiseless data. Anybody who plots noiseless data or talks about noiseless data is lying, right? There is always noise, and if they don't talk about noise, then they forgot about the noise, which is worse. They may contain more drivers than we know, and the noise need not be random. This is the part that I feel a lot of physicists and astronomers fall into. They always assume that whatever the leftover fluff in the data is, like the fact that it scatters around the line, is random. It need not be random, right? That could be a secondary effect, could be an additional signal. So there's always an XKCD for that. Basically, my class is XKCD based because usually there is a joke that works rather well. And so here, for example, if you do a model, you plot the line. We've looked at a lot of plots that look like the second one or third one, to the point that you start dreaming about the fourth one. We all know about models and plots now. The final grade, if you're an undergrad, you get a grade. If you're grad school, you basically get a pass-fail. But I'm grading everybody basically on this. 70% is the Jupyter Notebook, 20% is the final paper, and there's going to be those class notes. Because I'm not really sure if everything comes across, and so I would like you to take notes if possible, but I want you to take collective notes. This is a way to collaborate. And so I've put an overleaf link in the first assignment. There's a click on, you can click on it, you get to the overleaf document that we can do. I will go make an, I will present this in a minute. But essentially, I want everybody to take class notes. It's kind of like a Google document, but now you can do things like put a very complicated formula in there. Extra credit. Well, again, this is more for if you're an undergrad, but if you have a cool little Jupyter Notebook and you want to show me, please do. Right? I'm not sure if extra credit helps you here, but I totally want to see what you're working on and what you use Python for. Okay, so I have a question. If I have already talked about it, please, please look at these things first before you, overwhelm me with email. If the semester starts to really start to smoke on the edges, please let me know early so I can help. The more time you give me, the more wiggle room I have, right? If you come out the last day of the semester, I understand that that's us procrastinators leave it to the last minute. Again, if I can help you put out the fire better if you give me more time. So Python, again, XKCD for that. Why do we use Python? And who here has like more than several years of experience? Like who considers themselves like above average Python programmer? Okay. Why did you pick Python?
Well, it depends on what project you're using it for, but specifically for machine learning, it's top of the line. Like it's specifically developed for machine learning.
Do you know how old Python is about?
Say again?
Do you know how old Python is about?
I mean, it's recent. It's pretty recent compared to like some more hardcore like Java and C.
Right. So it's already 20 years old, right? But it was the thing that when I was a grad student, I had an excellent supervisor, and he basically said, hey, I hear this Python thing is great. Oh, can you program it? No idea. But I hear it's fine. The reason that he advised that I go use Python was for several reasons. Now, the machine learning modules are excellent, but they didn't exist back then. Python was great because it was rather easy to read. It didn't depend on parentheses or on semicolons at the end of every line, all that good stuff. And so it was fairly easy to read your own code again, and it was good with visuals. And then more and more modules were kept being added by different subfields of different sciences, including computer sciences, which later added the machine learning parts. But if I wanted a statistical analysis, there was a statistics package. If I wanted a scientific analysis, there was SciPy. If I wanted to do stuff with numbers, there's NumPy, right? There's these professionally maintained packages that I can just import and I don't have to worry about. So it's fairly versatile, and you can clutch stuff together that better programmers have already done for you. This is for me, was a really great thing because like I have to remember what the exact expression was for, let's say, a translation between Aryan deck to another Aryan deck to a position on the sky. That's gnarly stuff with cosines and sines and all that good stuff. Hey, guess what? There is a Python package for that. I don't have to go and type that in and worry about forgetting a sign. There's many different packages. There's a broad online community that will help you or mansplain to you, depending on how you phrase it. But there are very much subfield-specific packages. And so these things are, for example, developed for particle physics. There is a specific NumPy package that goes with particle physics, right? That used to be C, but basically they chucked all the gnarly C bits into a Python package, so it runs fast, and you can just import it and just give it to those functions. So as an example, but not surely limited to that, but I am the most familiar with something called AstroPy, which is exactly that for astronomy, right? It does all the specific stuff that I need an astronomy package to do. And so it is community-driven, meaning that multiple people have contributed their expertise to it. It is also community-checked, so that means other people have checked the outputs. It has got most of the core functionality, and it's got dedicated programmers now basically maintaining it. So it's got a few things, like, for example, units. Astronomers are known for having like really weird units. Light years aren't even close to the weirdest thing that we use. So having something that actually keeps track of what unit your variable is in as a physicist is awesome. It also helps you convert these. And coordinates, again, is that thing about, on the sky coordinates, nothing duller than trying to figure out, and nothing more frustrating than actually missing your target by like half of a degree. So we've all done that, or at least if you've been an observing run, then yes, you've managed to miss the target because of a conversion error. So having coordinates and conversions is good. And then time does the same thing for time, for universal time, etc. Table is sort of, who here has heard of pandas? Pandas, I'll run through a quick introduction, but that's basically where you put the large data tables in. Python has its own little table package, but it's sort of cute and not as good as pandas, I'll be honest. But yeah, we sort of use our own klutz together version of that, because we also use our own FITS. FITS is a standard astronomy table and data file from 1967, and we're still stuck with it. So we need it as something that could read it in. Open source and open developments means that basically anybody can contribute. If you're getting really good at this and go like, hey, there's all this useful functions that I have that other people could totally use, and I'm happy to write a little bit of documentation for it, and then you can contribute it to the Python program, the AstroPy project. There's all kinds, so that's what becomes these affiliated packages where I go like, this is really useful. Oh, wish I could actually have that just imported, and then there it is, right? So. And so the final is, then I know that you're done, so you write a little bit about either the visualization or something about machine learning, especially if you find something about how machine learning is used in your physics subfield, right? So you say, hey, I'm doing particle physics. This is how particles are being classified by a machine learning algorithm. We'll actually have a Jupyter notebook about that, but if you find a cool paper, please let me know. It can either be the visualization or the use of machine learning. Yeah, that's all. I usually did presentations for stuff like this because talking to other people is one more communicative thing, right? You have to do writing, you have to do oral presentations, and you do have to, visualizations are the three things that you get your point across. You have much less time than you think. Typically, people sort of zone out after 30 seconds, and the further you are into the conference, the further you are into the meeting, it's going to go down to like 10 seconds or so, if you're lucky. So having something where you can get your point across immediately. Otherwise, if this were in normal times, I would have everybody up here and talk, but I think a paper will do. So we'll talk about machine learning, AI, and big data, which are the three big buzzwords I feel for the last 2 years or so. AI sort of means machine learning as far as I can tell. And big data, really nobody has a great definition of big data anyway. The best one I've heard is that it sort of breaks normal statistics. So you can't do it the normal way. You can't do it the original way, right? So often, for instance, if you fit a model, if you're from my generation, you would look at the visualization, you look at the model, and go like, yeah, that looks about right. Like you check it visually anyway. You would never go like, oh, okay, well, we'll believe the algorithm. You never believe the algorithm. You always check it. Well, with big data, maybe I don't have enough eyes on the amount of data that I can actually do a reasonable check. So how to do a visual check of big data, as soon as that starts breaking, then it's like, then we're talking about real amounts. So if you want to do that, critically analyze a paper that talks about machine learning, preferably in a physics or astronomy context that you like. Okay? So what should go into that paper? The main conclusion, what's the strength and what's the weaknesses? I want to get you into the habit of reading a scientific paper. So you read it, you scan through it, you go to the abstract, you go to the conclusions, and then you kind of hop between the figures, and that's sort of your 5-minute read of a paper. But then the thing that should already start forming in your head is like, what's the strength of this? Ah, cool, they had new data, or they did this new analysis. What's the weakness? that sort of comes to the surface after if you read it a little more carefully. But that should become pretty clear if you do a proper read, right? And then what's the context? Like, is this a larger collaboration? Is this an ongoing project? Or is this something that this is like a target of opportunity? Target of opportunities happen a lot in science. Like, you just start with, hey, that's weird, or like, oh, well, I guess we're not looking at that thing because it's, behind the hills over there, so we'll think of something else, right? So sometimes the context is like, well, we had time, or we had some extra time at the end of an engineering night, and so we looked at this and it was fun, and we noticed this, right? So that often happens as well. Is it well illustrated? Is there like one figure? And typically, I want you to, if you're looking at a paper, there should be, doesn't mean that there is, but there should be one figure you can lift out and go like, that's the whole paper, really. So if you're writing a paper, you'll notice that it's like, my result is in this figure, actually. So that's the one that you should put effort into. So there should be a well illustrated, like, this is my result. This is my result in context. Like, here's the other groups found this point, this point, and this point, and here's our point, right? There's often a plot like that. Find it. And then how does it scale to new data, right? So especially with machine learning, and the reason that you'll find people who are slightly older than me quite blasé about machine learning is that we've heard this before. Some of these algorithms are 30 or 40 years old. They were going to solve everything in 1998. And the thing is, we did see a couple of papers go by, and they would all be like, oh, it does fantastic on all these spectra. Great, wonderful. So what was your training and testing and validation data? Oh, that's all the spectra we had. Are there going to be new ones? No. So it's like, what are you bothering me with this for? So now sort of moving to this machine learning thing is because the data is coming. Those papers were simply way ahead of the time, so like they did well with their training data, and they're like, look, it works. And then we all went, yay, now what, right? What's the next thing? And so many sciences, you can work in ATLAS, you can work on the Vera Rubin telescope, you can work on the square kilometer array, you can work on just about any physical science. The data is coming, or it's already here, right? So it is petabytes of raw data coming in. How do I fish out the signal? It is huge catalogs, millions of galaxies, lots of images. Or, for example, a complete digital image of the sky that's refreshed every week. Every week we have an entirely new sky image. And then we do it again, and we do it again, and we go look for things that blip and explode and all that good stuff. So suddenly the data's here, and now we need to do something clever. But so how does it scale? And does it scale? Right? And sometimes the answer is like, it doesn't. It works great for this very small niche, and that's it. Okay, so I like, for example, B.E.B. Du Bois was a fantastic example of data visualization. So I talk about, part of my motivation is to go like, why am I talking about data visualization a lot? Or why do I like Python a lot? Because it lets you do stuff like this quickly. So the neat thing is, bar graphs were a new thing in the 19th century, but it's still a very good way to visualize who owns what. Any particular reason why? Okay. And so mapping things. There's also Python modules that allows you to map things directly onto a line diagram of the state, for example. You can do things like bar graphs and curl them around. This is easier to do on pen and paper, but there's these use your information both as color and lines, like build degeneracy into the way that you're conveying your information. And so that's part of the visualization, right? You have people in your audience who are great with color. There are people who are not great with, seeing colors. There are people who are great reading things and prefer reading things. There are visually oriented people, right? So having a visual of your data, having a visual of your result is a good way to convince people, because it turns out many of us are pretty visual. So you can do things like, this is, I think, one of the very first visualizations. I think it's it was the sickness and casualties of the Crimean War, and basically it was one of the very first data visualizations where they showed, look, illness is a way bigger problem than the bullets, for example. Like, so you get a point across. This is is another typical example in data visualization, one of the very earliest ones. Napoleon's invasion of Russia. This is how big the army was at the beginning. It goes all the way into Russia, goes all the way to Moscow, and this tiny little trickle of people comes all the way back, right? It was a bad idea. So, never start a land war in Asia. And it's another quote from The Princess Bride. And so this is the kind of thing how you can visualize something, right? So these are these revolutionary, like, old visualizations. But you can think about what is the proper way to show the thing that I found. Because there's nothing more galling, really, that you found something really neat, and you can't convince people because you kind of used too small plot and too small letters, and they couldn't quite read, and then you, I don't know, you fail like at the 26th mile of the marathon, so don't. Okay, so these Jupyter Notebook assignments, you can do them on here. You can log into one of these machines. Use Teal09, password is Teal2016 U of L. You log in with your on the Wi-Fi, and you start one of these terminals. Who here has worked with the terminal commands on a Linux machine or Unix machine before? Okay, so yeah, it's sort of going away, but it's really super powerful. And so one of the things you can do is start this terminal, and it allows you to type in commands, and the computer will do the commands. So that's the prompt. You can do two things, and now this should say Conda activate Astroconda and then Jupyter Notebook. So if you type these two things in, it will start a Jupyter Notebook. Basically, you type that in, then say Jupyter Notebook, and then it'll pop up a browser, and then you can navigate to the files on the computer in the browser itself. And the neat thing is that there's little boxes in each Jupyter Notebook with code that you can write in and then execute. And you can execute them in order, or you can execute them out of order, which is not recommended. But you can just execute little snippets of code with text in between. So I have all these Jupyter Notebook assignments on Blackboard. They come with some data files, so download those and put them all in one directory, and then you can work on the Jupyter Notebook. If you are getting stuck on those, let me know. This is what Thursday is all about. I'm here to help you do these things. Effectively, this class should take you this evening and Thursday evening and no other time at all, right? Preferably, it's about an hour. It should be an hour for most people to do these things. If you're done early, great. And so you start the Jupyter Notebook, you navigate there, and then the i.pynb file is the Python notebook, right? So it has Python code and other stuff to show what it is. I think if you're in my 500 class, 590 class, or in my 390 class, you've done this before and you're now very bored. If you get stuck on this, let me know. And so if you install Conda on your own machine, you do Conda activate Astroconda. That's what you need to do now. And then you can say Jupyter Notebook, but make sure that you have Astroconda, because for very few things I might actually use Astroconda. The packages you will need in the second half. Look, I try to do these things with like a bog standard Python installation as much as possible, because then I don't have to worry about that. Honestly, Minisom, scikit-learn, especially scikit-learn, is a machine learning package that allows you to learn these things. Keras is another one that's being used for Python. This is all on the PDF that's on Blackboard already. I document everything, but yes, make sure that these things are in there, and TensorFlow. These last two, Keras and TensorFlow, you need for basically the last Jupyter Notebook. You don't have to do all the Jupyter Notebooks, by the way. If you get stuck and you're about 70% of the way through, great, you're done. But I want to give you the opportunity to learn as much as I did, preparing this, essentially, on these new techniques, these machine learning techniques, these new ways of doing business. If you need to install a package, pip-install. Did I misspell install? Yes, I did. And then a package that should install it on your Conda installation. Here's a thing to help me. Please, please, please put in your name somewhere. Every time there's like one orphan Jupyter notebook that I get that I have no idea who did it. So if you put it in the name up here and like here as well, so I just know whose it is, that'd be great. Okay. And so each cell is a snippet of code or markdown language. So basically I have like either Python code or markdown is basically just text. You double click to activate a cell and then shift enter executes it. So you can just run this code, and the neat thing for this, it's great for prototyping. So if you are trying out new code, if you're trying out a new idea, you can build it in here, iterate quickly, and it's great for things like, oh, you know what, the font size on my big plot needs to be a little bigger. You can futz with this forever. It's awesome. And so you can just loop through that, and then if you can do top through bottom to make sure that you actually do the whole thing right. This is important to remember, that if you can execute these things out of order. And if you've coded before, that's annoying, because you've always coded like it started at the top and it ended at the bottom. But now I can redefine a variable at the bottom and suddenly start calling it at the top, and it's awful. Don't do that. I spent an afternoon, because the variable z is very useful, so I defined it twice somewhere in my Jupyter notebook. And so basically it changed definition halfway through, and then I started back at the top, and it had a new definition, and it broke everything, and I couldn't figure out what I did wrong. It was just because, you know, I'd executed the bottom one and then started back at the top. So it's important to remember what you've executed in what order, or simply make sure you have variable names that mean something to you and are unique. So that helps. But anyway, that's the one thing that is annoying for us older folks, because I'm used to basically my code running in order, and now I can accidentally run it out of order. If you need help, I will happily assist you, except installing stuff. I'm no good there, as is Lutz. So if you're doing this on your own computer, great. But my recommendation every time is going to be just wipe the whole thing, reinstall Python, and reinstall the packages. That's how I solve my problems anyway. So that's as much help as I'm going to be. Okay, so if you're done, make sure you put your name in the file name and then upload it back to Blackboard. You can email them to me in case Blackboard throws a horseshoe or something. And make sure you log out of the Wi-Fi when you're done here. Just a little thing about good code. Good code is something you can read, which is why Python is so wonderful. You are the one writing it, though. So the number of times that I went, oh, I'll remember that, and then forgot promptly is way too often. So variable names that actually mean something, right, rather than z, which is, silly old me did. It's okay to leave comments. Comments are good. They're some of the best code I've seen. It was mostly comments. It was like, here's my entire thought process, a equals b plus 5, and then there's the rest of my no uncertainty there. So it's good to leave. It's good practice to leave yourself notes. The markdown cells are great for that. So I use Jupyter Notebooks now for research, and I put the markdown cells in between, saying like, and this is my reasoning, and this is the reference where I got this from, and here's where the data came from. It's a notebook. It's a research notebook. Okay, graphs should be. MS Paint was an abomination, but basically, some of these older, 1970s, 1980s visualizations are fantastic, and considering what kind of computers they were done on, it's pretty amazing. So a lot of that was simplicity, right? So as simple as possible, no simpler. Yeah, the class is being recorded. I just wanted to be very sure that you all know that. So the recording goes onto the Blackboard, so you can see this later as an MP4. The PDFs are on the Blackboard beforehand, so you can annotate on an iPad if you want, but preferably I want you all to summarize on Overleaf, which is what I'm going to demonstrate now. And so we've got everything online. You don't have to be here if you are exposed. There's already one of you that has been exposed and is now quarantining. I want to make it as easy as possible for everybody to do this online. That's it. Any questions? Everybody's sat here impassively with masks on, so I'm talking into the void as far as I know. Yes? So I can see who contributes to Overleaf. That's the nice thing about a shared document, like a Google document, right? If nobody writes, that's it. You need to contribute to the document. That's it. I want to encourage everybody to do that. Guess what? Overleaf is the way you're probably going to write your thesis. Overleaf is how you're going to write your funding proposals. Who here has written a funding proposal? He has. But you're not going to do that on just a Word document, right? This is going to be a shared collaborative effort, multiple people in multiple time zones, and that's why I want you to learn how to do Overleaf, because that is a complete game changer as far as I'm concerned. It is like a Google document, but with LaTeX, which has a couple of extra benefits. So I'll see if I can show that real quick. That's still not working. Here's one example of an overlay. So this is the going to make this a little bigger so everybody can read. So Overleaf is really just a website with projects on it. And the one that I was looking for, I can just book. Here we go. Look, I'm writing a book. That's great. Wonderful. Actually click on it or what? Here we go. So what it ends up looking like is this. You've got a bunch of files in the left-hand column. You've got text in the middle, and it generates a PDF from it immediately. So the text in the middle has a bunch of commands. It's very like a programming language, but it's got commands that say like things like subsection. So whatever the style is, put in a subsection which says this here. And part of the reason that I want to do this is class notes. Here we go. So I shared this document with other people, which is what you can do up here. So I just send the link to you, so you can all go there and put your stuff in. Just put your thoughts in, raw text, perfectly fine. As we're learning, this is one of those things where you can go, how do I do X in LaTeX? And look at that, there's a Stack Exchange about it. I have yet to come across a weird command in LaTeX that I have not seen an expert exchange on Stack Exchange that was like 8 years old, right? So usually this has been an exchange on Stack Exchange. Here's what happens. You've got a bunch of these commands. You're going to leave those commands alone. That's perfectly fine. Only when we get later in the game, you start adding things there. At the moment, you just scroll down in the middle here and go blah, 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 don't care, don't care. This is all packages and details, and this is what I want to happen here. You have got everything under control. But here's a title, add your name. It does a few things more, and then begin the document. This is where we start talking. And so there's the introduction, and you go like, hey, we just talked about the first class. I found the first class extremely dull, and I nearly fell asleep. Great, fine, first note's there. That then compiles and becomes a PDF. The reason that I like this is because we can do things like make title and table of content. Is that the actual one? Does it work in this one? Not yet. Okay, I'll fix that later because real time never works. But what you can do is basically have a table of content that dynamically updates on the PDF all the time. So you can actually have a table of content super easy. You can have things like references very easily. So you can do things like, here we go, you can do figures, but it goes like here, The Hitchhiker's Guide to the Galaxy. Again, I'm showing my age here, but you do cite The Hitchhiker's Guide to the Galaxy, right? And that's your dynamic citation, because here in the references, it shows up. Actually make this any bigger. No, just that, okay. And here in references.bib, you've got these bibtech ways to keep tabs on the different kind of references. Now, this feels very elaborate, right? Who here has used EndNote or any kind of citation manager before? Citation manager? Yes, there's something called the citation manager. If you're writing something as big as a book or a thesis, you've got more than 5 citations. You've got hundreds of citations. You need to keep them all in order, and you need to make sure that you don't accidentally, mix them up. So this is where you put the books and other things, for example, in files like that. A lot of ways to search the literature will spit those out for you. You never have to write these things yourself. There's like at the bottom you say like, oh, here's the EndNote file for it, and then you can import it into EndNote. EndNote is the one that you use with Word. In the case of LaTeX, you use, in my case, BibDesk, and these are the .bib files. That's the way how I keep my references separate. I have a huge bibliography file. Boink. And I use BibDesk to keep them all separate. You can't read this, but there's several thousand in there, and they all have these like little reference files. So I just upload that into Overleaf, and I can just cite, myself or other people, preferably other people, and that's how I keep my citations separate. And it will keep a track of which ones I've cited in this particular document, and it will make a ordered list at the back. Because that's dumb stuff, and you should have a computer do that. You should not go through your own 400-page thesis and make sure that you've got every reference in the end list. Because of course the professor that you failed to cite, somewhere is going to go through the list and go like, wait, why are you not citing me? And then get all up in your hair about it, right? So the thing is, I love this because it takes that out of my mental space and it just does it for me. And I don't have to remember, I don't even have to exactly remember what the guy's name was. I just have to remember the first few letters, and then it actually auto-completes for me. It's great. The writing goes a lot faster. Okay. So I can start talking about this. Depends a little bit on, a little more time actually. So I'm not used to this hour at all. So if this is not a good hour for anybody, let me know. But otherwise, welcome to 650. I can go into the second lecture now, and so we can just get that done. Cool. Okay. Everybody okay with that? I just saw one person nod and just ran with it, but okay. So this is the second part. What I would say is the second part of research, which is really just yes. No. Oh, sorry. As soon as I see anything over the heads, then I just sort of assume it's a question. And so, how do you do a science, right? So this is sort of what research method is about. And so there's a few things that you're learning hopefully here, because I never got a class about that. It was sort of like, well, you just pick that up by osmosis. And some stuff you will pick up by osmosis simply because you teach each other, right? That's part of this. But the state of, like, what do I figure out? What is the state of the art, right? What's the bleeding edge of my field? How do I get reliable information? and how do I present that research then to others, right? So there are roughly 3 kinds of you, or at least in astronomy. There's observational. There's people who are basically in a lab or at a telescope who get data. There's theoretical, people who model things or, you know, even write out equations for cosmology. That's sometimes still good. And then there's instrumentation. You actually build labs. You actually design equipment. So this kind of goes for both physicists and astronomers. Have you picked what kind you're going to be? Or is this like, I sort of have a feel that that might be interesting? There's lots of overlaps, right? But these are sort of the 3 that we talk about in astronomy. You're an observational astronomer, you're a theoretical astronomer, or you're an instrumentationist. But there's a lot of overlap. A lot of people are observational and instrumentation, because as soon as you fix the widget or built the widget, you're going to go, you know, duct tape it to your telescope and try it out. And then you're an observational astronomer. So the how-tos are how to carry out the research, what kind of researcher does, and how to present your results to others. This is sort of the career path. Master's is what you're at, 2 years, a few years of PhD, postdocing, and then I do this until I'm retired. This is from PhD Comics, and if you haven't seen this before, this will get you through your PhD, trust me. So, for example, the scientific method is, this is how we get started. We have a hypothesis. Or we have a question, and we're going to go formulate a hypothesis. What is the moon made of? We've got this thing here in the sky. What's the moon made of? Anecdotal evidence suggests that it is made out of cheese. Both children's songs and others have told me that this is very cheese-like. Okay, the hypothesis. I think the moon is made out of green cheese. Cool, let's go check that. How do we do that? First, we do an experiment. We test the spectroscopic response of cheese in the lab. All right, now we have something to compare against. And so we will now use a got a spectrum, so we got a reference point to compare to. All right, the scientific methods. And so then we go and report the application of near-infrared reflectance of cheese, and then analyze the result and go to the conclusion the spectrum does not match outplay. Now, if I just change the cheese words, you can see that it's Dutch cheese, but if you change the cheese words with any other astronomical object, this would be a perfectly sane thing to say. This is how you check that. And so as soon as it fails or is falsified, you try something else, right? Or you reevaluate whether or not cheese should be in your life. And so that's the scientific method as you may have encountered it earlier. And so you just construct a hypothesis, test with an experiment, analyze true, false, write up results anyway. Especially false is sometimes not written up. Something called a null result, basically, like, well, we couldn't quite tell, is often not written up. And I can tell you that you will do the rest of the scientific community a favor if you make sure it's in the literature anyway. Because then they can go, oh, wait, you already tried that. There's a famous astronomy professor called Tully, Tumra, and the Tumras, 2 brothers, usually would have a dynamic result for a galaxy problem already. They went like, yeah, it wasn't that interesting, so I didn't write it up. It's like, well, then it just lives in your head, and I have to go find it out again. So write up the hypothesis, true or false, write up the results, present them, and if it's false, try again, right? So then loop it up. But this is an important part of the process. So how do we tell that to other people? Talk to them directly. It's not cheese, okay? Talk to them in a meeting. It's not cheese, okay, but cheese. And then write an academic research paper, right? So that's the way to communicate it to the rest of the world. And so how do you tell others of a discovery? Honestly, yeah, sure, you can use all kinds of Google and Wikipedia and everything, but really the way it goes, meetings, that's how you present the most recent results. Now, of course, all of this stuff is over Zoom, and I hate it, but that's fine. You give talks to conferences on your results, partly to get feedback from the room, right? Because there's always something that somebody has thought about that you simply missed. And so that's really helpful. And then print it. And so how do you look for reliable information? And then how do you present it? So textbooks take many years. So you can start thinking about these things as with a duty cycle. Textbooks get renewed, well, okay, fine, these 100 textbooks get renewed every year, not because there's new information in there, but because that's how we print money. Sorry. But academic textbook, typically, it takes us a few years to actually compile all the information and then stick it in a textbook. A doctoral thesis takes several years to write, and that's, while that is the latest and greatest, it's still, got a duty cycle of about 2 to 4 years. That's typically more like the last month. And then preprints is really what comes every day. Researcher, you'll get into the habit of looking at a preprint server on what the latest information is. People are allowed to put everything on the AstroPH in the case of astronomy. There is anywhere between 60 and 90 new papers a day. So yeah, research is moving along, but you do need and so the PhD, the doctoral thesis, that is a huge body of work, right? That's the thing that we're working towards here. 4 years in Europe. It depends a little bit what kind of institution you are here, but a PhD takes about anywhere from 3 to many years, although I do not recommend the many years part. Okay, so how do we communicate the results? There's only a couple of real physics, astronomy journals. There used to be many more. Basically, every observatory, the Royal Observatory of Billund had their own paper, right? It was basically all the letters that were sent to the director, and then the director liked it and stuck it in the paper. That's no longer how we operate. These are operated by societies. They have professional editors. They have professional staff. It's really just the astronomical journal and the astrophysical journal. Those are the two in the US. The multi-notice of the Royal Astronomical Society is the one in England, so you have to spell in British. And then there's Astronomy and Astrophysics, and that's the European one. And then sort of end the list. You can also publish in Nature and Science. Those are kind of like more broader. They're very expensive, so unless it's like a huge deal, you typically don't. SPIE is if you work in instrumentation. That is if you build a new telescope widget, that's what you report in. It's a professional association of engineers. Physics is basically you've got PhysRev 1 through X. I can't remember what X is anymore, but those are kind of where you would publish your papers there. But it's very much, it has a very specific structure. This is very typical for any scientific paper, so I can use the astronomy as an example, but I've seen others, and they follow the same structure. They are written in plain but accurate description. It's kind of dry, I will admit first. They are very much this and this was combined in this way, and there's often a lot of specific wording that people use. There's a lot of jargon. Try to avoid it. But it's very hard to do because, as soon as you start talking about, I don't know, the various bits of your setup, you have like abbreviation for the giant big camera, for example, and then you call it the GBC for the rest of your paper because, writing out giant big camera is too much work. And before you know it, you talk to your grandma about the GBC, and she has no idea what you're talking about. So it's really helpful if you at least explain your abbreviations. And so very clear but sort of dry way to talk about it. So what is in papers that appear, right? You've got a title, you've got the authors, the people who worked on it, and the abstract. And the abstract is the first thing that you sort of read, but it's the last thing you write. It's the absolute last thing you write. It's sort of the summary of the whole thing. So only after you've finished your paper, you write the abstract. There's an introduction, there's a method, there's a result, there's a discussion, there's a conclusion. It doesn't matter what science I'm in, those are the elements that are going into my paper. The method could include things like, we got data at this telescope on February the 12th, but we can also go, we went to Atlas and we got, the cycle 15 Atlas results. All these things like, where did the information come from? this is what we got, and here's what we think had happened. But the introduction is the part where we go like, here's the problem, here's how we tackled it, there's our result, this is what we think happened, here are our conclusions in a neat little summary. Go away. Okay, so the introduction is the general statement. There better be a question in there. So if you're reading a scientific paper, there has to be at least one sentence in there somewhere that is the central thing you're trying to tackle. If I'm editing a paper for colleagues, it's usually the thing that they have left out. I go like, hey, so what's the thing you're trying to answer? It's such a thing. You've been working on this for like 4 months, right? This has been a long experiment. Is the moon made out of cheese? You built the spectrograph, you made the comparison, you made the plots. You've been working on the is the moon made out of cheese question for months now. You forgot to put it into the introduction. It's a very simple thing. So it's like, make sure that the central question that you're trying to answer is not just in the abstract, but also in the introduction and why this was important. The method. This should be detailed enough that you could recreate the actual experiment. Detailed enough. That means we use this filter for this spectrograph with this grading setting, and not anything like, we had coffee this morning, not tea. You know, it's the relative and details. But it should be enough that if I go to the same telescope, I should go, I want to observe this in the same way. Or I can go to a different telescope and I go say like, yeah, I need to be in this wavelength range and at this resolution. And I know I need to be, I need to look at this thing for at least 3 hours. So those things need to be in there, right? Those are the relevant pieces of information. The results, this is basically the meat of the paper, usually graphs, tables, what did we get? And then the discussion, that's more, so declarative statements, and I can be actually extemporate a little bit more. As soon as you go, I could phrase this as, I think this means it shouldn't be in the results, it should be in the discussion. So often as not, you just kind of, you write your thing, and then, for instance, you get to the results, and you go, you start having opinion, right? How could you not? You've been staring at this particular thing for months now, so you have strong opinions. If not, then you're pretty cold. So you've got this like opinions about that, and you need to kind of shove those over to the discussion, because that's where they need to go. And the conclusions is the part where you just sort of list what in more of like bullet points what you got. References, super important. All the stuff that went before, right? I am standing on the shoulders of giants. Well, this is where you quote the giant. Giant 1, giant 2, giant 2, 3. Make sure that all that stuff is in there. Okay, people lie on the time. How do we tell the truth? Well, first the paper goes to a journal. The journal has an editor who reads, kind of skims it, who's more of a generalist, right? So he's the kind of person who goes, well, I've heard of stars, so that's probably important. And they'll go and find somebody who has done something very similar. And they'll use things like, what is the big words that this person uses a lot? Or what are the keywords? And they'll figure out where this needs to go. And so they'll have they usually have a couple of software tools as well. And they get a list spit out, like these are people that have written about these words before, for example. So it goes through this referee. The referee reviews your paper and criticizes it. It accepts. This never happens the first time. Never happens. And it is really frustrating, right? This is a part where you have been at this and possibly trying to break this rock with your forehead for months now, and you finally have your result, and then this random person comes back and says, nah, because those are the most likely, except with revisions. Basically it says, yeah, but you need to do these things. Yeah, but I'm missing these things. This is why it's great to have like other authors help you with these things, because they can sort of do the refereeing process as well. Reject happens a lot for things like Nature. If you write a Nature paper, they reject 9 out of 10 papers, just because they can. And so, yeah, they reject a lot. In other fields, this happens a lot, for instance, in brain science and psychology and in medical fields. There is a ranking, there's a pecking order. And I'm so glad that astronomy doesn't do this, because basically they're all sort of equivalent. But there's like, this is the best journal, and if they reject it there, I'll go to the next best journal, and then to the next best journal, and I think my soul would die somewhere around here, because that was just awful. Anyway, not the way physics and astronomy is organized, so score for us. Basically, rejection happens a lot less in physics and astronomy. It does happen. I have had to reject papers simply because they didn't adhere to, I couldn't, for example, reproduce the results if I wanted to. It was that badly described. And if you then, somewhere in the revisions, don't tell me where you got this information, despite me asking politely, at some point you have to go like, I don't think this is a real thing. So out it goes. You have to do these things. A referee report are, typical number of revisions in astronomy is 10. So if you want to know how fun that is, you should ask Sean, if you know Sean. Sean finished doing this for the last 6 months, and he got 6 reports, something like that. Basically, back and forth, back and forth, back and forth, until he got everything right. Every I dotted, every T crossed. You're thoroughly sick of this, personally speaking. Rejected, angry, too bad. It's an anonymous refereeing process. This is true for other things as well. Things like telescope time is a competitive writing exercise. Beam time, all these things you need to propose. It goes to a panel. It goes to a referee. Accepted, rejected. You can be all angry, whatever, vent as much as you want. It is anonymous for this reason. So, documents can be your notes, or research proposals, scientific papers, and a thesis. So my advice is pick a system you trust and then trust that system. My research advisor told me that particular line in our second meeting, I think. He had a giant drawer full of physical paper in alphabetical order. That was his system. He didn't suggest I do his system. He suggested I pick a system I like, and then especially I trust, and then stick with that. This has become a whole thing for parts of the weird internet, the nerdy internet. It's called a personal knowledge management. Is PKM? Oh, personal knowledge management system. Anyway, comes down to you need to read a lot of papers, and you need to keep them somewhere. And somewhere could be under your mattress, but I do not recommend it. There are professors who have like these. I had one that had like 3 desks with all about 5 inches of paper on them, and he knew where everything was. Good for him. My brain would explode. So pick a system that you would trust and stick with it, right? So stick one document mode as much as possible. Stick your literature as much as you can into one system. There's Mendeley, and preferably something that backs up. Has anyone lost a computer? Has anyone had their computer stolen? Has anyone bricked a computer 2 weeks before their thesis was due? Okay, backup is your friend, people. It really, really is. All right, so the literature and reference manager is key. So you need something that backs up as automated as possible. Version control. If you have somebody that works with you and that says, hey, I've got comments on version 2, and you're on version 3, it's really fun to go find out which things you've changed. And it turns out that section 2 is now section 4, and so their comments need to be going there. You spend running after yourself more than you actually fix the problem. So version control is another one. Ease of use, because if it's too hard to log in, to use, to whatever, you'll never do it, right? You go like, oh, but I'm a very organized and good person. Yes, but it's better if it works when you're tired and it's due tomorrow and all that good stuff. And find a way to reference all the figures, and this is why you like LaTeX. So I did this forever. Who remembers getting like, this is final version 20.3, and then emailing back and forth? Don't. That's all I have to say, especially about theses, because you'll have your entire hard drive littered with versions of your thesis. You can number them. That works for some people. But sync, that's much better. And then especially the backups. Something off your computer, physically off your computer. Clouds are great. Cloud is wonderful. I had just basically had a time machine hard drive at home, and that I just plugged in at the end of the night, and then it would. And that's why I still had a thesis, despite that my laptop bricked itself. Our IT person had this basically hanging on his door, because, oh my God, this is really important. There are horror stories of plenty of people who basically burnt their only copy of their thesis, and well, that was it for 4 years. Sorry. So Word and Google Doc are one way to do this. Lots of people write in Word and Google Doc because it's ubiquitous. You have this already. You can get in there. The low entry learning curve. For less than 100 pages, that works great. But the reference managers exist, although I have no idea how they work with Google Doc. You'll have to go find that. But the version control is on you, and you have to, it sort of really starts doing this as soon as you get to thesis size, and you really don't want to transpose to a new system when you already have 100 pages or so. This was a meme. No? Okay. This has happened to me, basically, well, apart from the science part, is this really like, I had a huge Word document, and yeah, as soon as you move one document, it just suddenly has 5 pages extra that came out of nowhere. Which is why LaTeX is my preferred way to do it. Mathematical symbols are much better. Dynamic referencing, scientific standard. That last part is important. That means that there's templates for you to just pour your text into. You can go to the monthly notices, and they'll go like, here's your LaTeX thing. Just put it in there. Standalone still needs version control, but it has a steeper learning curve. So when you do your thesis, when the day comes that you start thesis.doc or mythesis.doc or what have you, that's when you need to decide which one of these two you're going to pick. And you'll have a good feeling of, hopefully, what's going to suit you. Okay, so that's where I did the overleaf example, or I was going to do the overleaf example, and this is why I want to do the overleaf with you for the class notes. Does that make sense? So you at least have a feel for it. You've tried it once before. You hated it, and then you went over to Word and hated it even more, right? Sometimes it's that, and so that's the overleaf assignment. The assignment is to take class notes, even if it's like, yeah, it was fine, that's fine, but stick whatever you found in there. We can include figures, references. We try to organize it in a chapter each week, and it's a communal activity. I find this really worked in other classes as well if we all take notes together. So, literature. Somebody has done this before, and there is a fantastic thing in chemistry which basically says several weeks in the lab will save you half an hour in the library. If you have a cool idea, the first thing you need to do is make sure that nobody else has done this before. First thing, because chances are that, on the whole field doesn't remember much beyond 10 years ago. And some smart kid in the 1970s did it, or the 1980s, or the 1990s, or what have you. So go back and see if anybody has done something like that. In very general, I use scholar.google.com. That works okay. It gives me completely different results than the this is kind of astronomy specific, the astrophysics data system, ADS, but it does now include physics. So I found physics friends in there they have all the references in there as well. Hydrology is in there now too, so I know that because there's apparently, I share a name with a hydrologist. So if I look on my own name, it's like, oh, I've done something in Sudan. So it's a good way to find people, but also topics and references. So these reference managers, I'm talking about EndNote. That works with Word, I've heard. Mendeley is something that's sort of online. Papers is another similar thing. This I do not recommend. And BibDesk is the one that I use. It doesn't matter which one you use. It matters that you pick one and stick with it, because there's nothing more heinous than trying to translate one to the next. But that's what this BibDesk was for, where I have not just, I have a little search bar up here. Let's see if I can actually make this bigger. Can I make this bigger? Okay, well, I'm not anything but as self-obsessed, so I'll type my name up here, and these are all the, these are some of the references I've been in. And so it has a little key, my paper from 2018, the title, when it was published, all the authors, all that good stuff, and it has a link to the PDF. So I have all the PDFs nice and local. I'm all organized. They're all in alphabetical order, and it is a bib file, so I can actually import it into my LaTeX. So this kind of stops me worrying whether or not I have the paper. It stops me worrying where I have this. It's in here. When I started the thesis, I had 5 or 6 of these bib files littered all over my hard drive, and then it became more and more, and I couldn't figure out where I had that one reference in. So just keeping it all in one spot. Mendeley does the same thing. EndNote can do the same thing, but have like one file where all your references live in. It's such a small thing, and I spent 20 minutes talking about it. I feel that strongly about it because I messed up at your point, and I sort of had it all in a big mess. And as soon as I concentrated it in one file, my life became so much easier. Having to run through a bunch of these different ones, figuring out which one I forgot about, is not the way to live. So if you want to keep your writing, the end part, the thesis writing, is tricky and hard and stressful. This is one of the ways to keep less stress in your life. So that's, a little life hack that I found for science writing. Who here has used a reference manager before?
I mean, does the big messy pile of printouts count?
Yeah.
Yes.
Because that's how we all start, right? It's a very organic process. Reading papers start with here, read this paper. Oh, cool. Who's this person? Oh, they've written one. And then you have 2 papers. And then you have 5. And it's sort of an exponential process. And then you have a nest that you can, it's nice and warm. So I've done that, right? My first literature review, and literature reviews are sort of fall down the various rabbit holes. That's perfectly fine, by the way, right? You read, and you read around the topic. You kind of see references that people refer to and go oh, that paper and that paper both refer to that paper. So that must be important. I'll go read that. There's literally, you can spend your entire PhD doing that. So if you have a good supervisor, at some point they'll go hey, so have you resurfaced yet from your nice little cozy nest of papers to make sure that, we now move on. The neat thing is that take notes, take ample notes, because when I got started on my thesis, first thing I did was wait, didn't I 4 years ago take ample notes? I did. Where is that? And I found a little LaTeX file with the bib file that went with it, and that was my, everything that everybody had ever done before that I could find, between parentheses that I could find, on the topic that I was going to work on. And that turned out to be 13 pages of the PhD thesis. And I'm like, yay! My thesis went from 0 to 13 pages in day 1. It never grew that fast since, because it's hard to write scientific prose, and I am not the fastest writer. So make notes, do this right at the beginning, do this early. And you know, that could be like a little working document. They don't need to be good structured sentences. Punctuation is entirely optional, right? This is things like, so-and-so found this, and they didn't agree. There we go. I don't agree with either. Moving on, right? It's notes, right? I can turn them into real prose later, right? Notes, 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 notes. But keep notes of that. I did it in LaTeX, which really saved my bacon because it turned into like my introduction in no time at all. Turns out you have written parts of your thesis already. Just make sure that you haven't accidentally thrown them away. Okay, so you can do, I use ADS a lot, right? So this is my, who here is planning to do astrophysics? There's quite a number of you, right? But there's also a few of you that do physics, yeah? So we can also do physics in ADS, but ADS is the main crutch as far as finding papers. So can everybody read this? Probably answer no. It's really just it's Astro Google, right? This is where I'm going to find something, but it has a few search terms like author. And so let's do this. Knabel. Let's find Sean. Oh, that sucks. Returned. Oh, no, there's 39, right? So there's a bunch of different people who are named Knabel because I didn't specify a name or anything. And here is their references. And so some of this is like, yeah, that's the one that I was after. But how to proceed with asymptotic modular dual taper HIP systems in case of acetabular revision. No idea what that means. Literally could not make it out of the title. Very typical for research papers. Which apparently has a Knabel person in there as well. And then here's Sean again. So we can read. I want to see if I can make that bigger. You can sort of read that at the top here. Here you go. This is called a BIP code, and it's usually a unique definition of all. So you can actually find it again. You just need that number. 2020 is like, that's the year. AJ is the abbreviation of the kind of journal. 160 is volume 160, page 223. And so BIP codes typically are built up like that. And so here's a link that we can actually go like, hey, let's see Sean's paper. It comes with title, everybody's on there. Here's the abstract, publication, Astronomical Journal, volume 160, issue 5, and then the page number. Here's another way that you can find them, a DOI number. Who here has actually encountered those before? One or two has worked in a library, yay. Okay, so that is a more generalized way of finding a document. As soon as it's published, it gets a DOI, which is a unique identifier for a document. It means something like unique identifier for a document, but I don't know what DOI stands for anymore. But basically, that's another way to find this particular paper. So it all gets all these labels, and the archive is basically, that's the preprint that we found that went with it. So preprints happen before or right after acceptance by the referee. To be sent my photocopy my paper because I'm so proud of it, right? That was the press, pre-print. Of course, we don't print journals anymore because we don't hate trees that much, but we still do the preprints. We actually stick it on a server, and that's as soon as it's done, as soon as I've submitted it to a paper, and I'm going like, the referee can't possibly have any problem with this at all. This decision will never come to bite me in the near future. I will put it on there, and so people can read it. The good news is, and so there's two schools of thought on this, right? Do you send this around to everybody? Do you show this to everybody before the referee even comes back with his or her report? Or you just kind of hold your cards and wait until you've fixed every last little thing that the referee liked and didn't like, and then put it on the preprint. That's a completely personal choice. Now, so on the one hand, you kind of go like, I'm going to make this as perfect as possible and only then show everybody. And then there's the, you know what, maybe the referee is an idiot, but I would like feedback from other people as well, and so they stick people. So there's two schools of thought in astronomy, and it's a completely personal choice. But, you know, again, as soon as you have a paper and you go like, yeah, I've sent it to the journal, you go like, well, I could just chuck it on AstroPH. That's fine. So that's the archive. There is many different kinds of preprint servers. This is the astronomy one, but there is ones for psychology, geology, physics. Everything is on there. And then the bib code gives us the unique identifier as well. Depends a little bit, and then we can export our citation in the different kinds of formats. We've got BibDesk, we've got EndNote, which, you know, looks differently. And then we can look to, you can even do custom formats. Those are all the different kinds of ways that you can have your reference appear. You can put them manually in LaTeX if you are feeling self-flagellate like that, or you can have something do it for you. Okay, so I'll happily show how that works. But in the meantime, so we've got an abstract, and then these are the references in the paper. This is why this is so wonderful, because all this stuff is already in here. I don't have to go, okay, AbJ, volume 202. I'm going to really date myself. I know actual physical libraries, and I've been there. And so we had these like giant rooms with huge rows of volumes of the Astrophysical Journal. And every month a new one appeared, this yay thick, and it would go clunk. There we go. And so I have gone in there, found the right volume, got it out, went to a thing called a photocopier, and then actually made a copy of the thing. Here we can go, okay, there was a reference in here. Where are we? Oh, this is doing this weird thing again. Here are all the references that Sean talked about, and here's that paper from Adam Bolton from 2004. And there it is, and if I want to see any detail in that, I can just go and look at that. So you could just go down the rabbit hole with links now. So this part is wonderful. And of course, because we're a bunch of data nerds in astronomy, we've also done things like, oh, come on. Metrics. Graphics and metrics. These are the figures in there, and here are the metrics of the paper. And people talk about this way too much. These are things like how many people have read this, how many people have cited it, over what year, right? So you can actually see how successful, quote unquote, the paper is. So you can get things like reads. Which one is this? This is the, oh yeah, this is the other one. So I'll go for Sean's. Here we go. Sean's paper. It's a recent paper. Let's see what the metrics look like. Well, it's been read a bunch of times in the year it came out. Okay, so, you know, take this with a grain of salt. But you can get all kinds of other things like author networks, word clouds, all these fun things, because people, you know, papers become data, and then people start playing with that. There's also ways now that machine learning literally goes, oh, you like this paper, you will like this paper, this paper, this paper. So yeah, there's many ways to fall down the rabbit hole. Please don't too much. But I'll talk a bit about the preprints. So every day, new preprints appear. If you have submitted right after 8 p.m. Eastern Standard Time, 8 or 9 p.m. I don't play this game, but people apparently do. They submit right after the deadline, and then you appear at the top of the next day's page of preprints. If there's 80 of them, maybe that's a benefit. But they can be accepted or submitted. And if all is well, you've put that in there, but it doesn't need to say that anywhere, right? There's some moderation. People actually look at, if it's not too crazy, it's like it's aliens guy doesn't get to post here. But most astronomers get to post their information there. So I usually get my latest papers there. I look that's where the news is. And so that's what it looks like. You have the reference number, you can get the PDF. PDFs are all free. So if you're outside, let's say, the university domain, this is where you can get the latest version of the paper for free. I'm a big fan of that for that reason alone. And so you have astrophysics, condensed matter, general relativity and quantum cosmology, high energy physics, 1, 2, 3, 4, 5, mathematical physics, nonlinear science, whatever that is, and nuclear experiments, nuclear theory, physics, including accelerated physics, applied physics, atmospheric and oceanic physics, atomic and molecular clusters, atomic physics, biological physics. Wow, every flavor of physics and quantum physics separately, because, ick. And so if you have a particular field that you are interested in, this is where it will be. And so at some point at the end of your thesis, as you're getting, as your papers start to appear, if you start actually putting your papers on the preprint server, you start reading these almost as a daily thing. You get the email digest where you go like, plump, there it is. This is what's new today, and go read them. And so this becomes a habit, right, to keep up with the literature. It can be a daily thing, could be a weekly thing. Yeah, I like, new is this today's, recent is like this week's. So you can make it like a habit. So that's what I do in order to keep up with the news that isn't, the news, because that can be distracting. By the way, if you are distracted by the news right now, because, we all are, that's okay. Let me know if you're struggling with the assignments or anything like that. So I'll talk about writing. Oh gosh, I'm 10 minutes overtime now. I'll talk about writing next time. Basically how to write, how to make it a habit, how I do it, because I struggled with writing, and most of us struggle with writing. And if you're not struggling with writing and you say you don't struggle with writing, you're lying. Everybody struggles with writing at some point, but we can get through it. And so how to write a thesis, how to do writing. That's part of research, people. It's a bigger part than I would have cared to admit earlier, but yeah, that's very much true. So I'll talk about that next week. I'm sorry to keep you 10 minutes extra on an evening. Somebody send up a flare next time I do that, okay? Then I'll chat to you next week. And you can be here, or you can be over Blackboard Collaborate on Thursday, right? To work on Jupyter Notebooks. So if you go like, I got this, that's cool. Put in the Jupyter Notebook. If you're stuck, I'll be here to help you out, or I'll be on Blackboard Collaborate, whatever is most convenient. Cool? Hey, welcome to 650.